Yeah, so is everything clear? You guys can see my screen, my audio, my video, everything. Is my screen visible?
Yes, sir.
Okay, fine. Yeah, so we can get started. So in the last class we saw the basics. I mean, we saw what a linear transformation is. We saw some of the examples. So from this class onwards will be looking at the portion that is given in your syllabus. So we will start with something which we call as linear function. So this is the first topic that we are going to study. So what is a linear function basically? So in simple sense, a linear functional, so we saw what a linear transformation is, right? So okay, so I can just go back. So we saw that if we had two vector spaces v1f and v2f, and we define a function from v1f to v2f with some properties, and if they satisfy those properties, we said that okay, T is a linear transformation or a linear map. So here also we can see the term linear, right? So what is the definition of the linear function? So it is nothing but a linear transformation from the vector space to its field. That is, if v over f is a vector space, so v is the vector space, f is the underlying field. Normally we take the field as r, because in your course normally we take f equals to r. So this is a particular case, okay, that is why I am not writing it in the definition. This is a particular case when f is equals to r, which is for most part of your syllabus f is going to be equal to r, but it need not be true in general. F can be something else as well. So if v over f is a vector space, okay, then a linear map or a linear transformation from where to where? From the vector space to f, okay, is a linear function. So basically linear transformations we defined on two vector spaces, right? v1 of f and v2 of f. Here what we are doing, in the place of this v2, the vector space, what we are taking is the field, okay, and when we take a linear transformation from a vector space to its field, okay, and if that map is linear means if it satisfies those properties, we say that it is a linear it is a linear function. Okay, I think I am having some trouble with this. Yeah, so that is to say, so if T is my transformation, if I take alpha x plus y, this should be equals to alpha time t of x plus t of y, where this x and y belongs to the vector space V, okay, and this alpha belongs to the field F. So this is what is the definition of a linear functional. So essentially you can see that it is nothing but a special type of linear transformation. So in linear transformation we used to have two vector spaces. Now we have one vector space and one field. Now one thing to note here, that I am sure that you all know, that a field over field is always a vector space. Okay, and the dimension of this f over f is always 1. So for example, I think you have already studied this. So R over R is a vector space, and the dimension of R over R is nothing but 1, because obviously it can be generated by a single element. Okay, so this is fine. Now so let us see some examples. Yeah, so we can see some examples of linear functionals. So we saw in the last class that we defined some transformations from the set Rn to R or Rn to Rn, right? So now if I take a transformation f from Rn to R, okay, such that this f of x is equals to a1 x1 plus a2 x2 up to an xn, where my x is some vector in Rn, that is x1 x2 xn, for some fixed a1 a2 an. Now this is actually a linear functional. So okay, so we can, so for a better understanding, actually we can take a sub example. So let's say that I have a function from R2 to R. Okay, so here n is equals to 2. Now any vector in R2, how does it look like? It look like some x1 comma x2, right? And let me just define a1 equals 1 and a2 equals 2. So we can take actually any a1 a2, it is our choice. And what I am defining is f of x is equals to a1 x1 plus a2 x2. Now this is a linear functional. So if you want, you can actually check it also, because how do we check whether something is a linear functional or not? So we check that if f of alpha x plus y is equals to alpha time f of x plus f of y or not. So this is what we have to check. Okay, and where alpha belongs to the field, in this case the field is the R. So okay, we can check. So let me take the x vector as x1 comma x2, y vector I am taking as y1 comma y2, and alpha is some number that is in R. So what is my f of alpha x plus y? This is going to be nothing but alpha x1 comma alpha x2 plus y1 comma y2, right? Now if I simplify it further, what am I going to get? I'll get alpha x1 plus y1 comma alpha x2 plus y2. But how I have defined my function? So for any f of x, our a1 is equals to 1 and a2 equals to 2. So this is equals to a1 time, now this is my, this first vector is my x1 and this is my x2. So a1 time of x1, that is alpha x1 plus y1 plus a2 time of alpha x2 plus y2. This is how we have defined. Okay, so we can just say because f of x1 comma x2 is equals to a1 x1 plus a2 x2. Okay, but now this is equals to, what is our a1? a1 we are taking as 1, a2 we are taking as 2. So this is equals to 1 time of alpha x1 plus y1 plus 2 time of alpha x2 plus y2. Now I can write it in a different way. So what I can write is, I can write alpha x1 comma 2 alpha x2, right, plus y1 comma 2 y2. But now this is actually, if I take alpha as common out, so I'll get 1 time of x1 comma 2 time of x2. Sorry, this is not a comma, obviously, because it is a linear function, plus, right? So this is also plus, this is also plus. So this is y1 plus 2y2. So this I can write as f of x1 comma x2, and this is f of y1 comma y2. So what we got is f of alpha x plus y is equals to alpha time f of x plus f of y. This is what we have to actually prove. So this is just an example to show that any linear transformation of this category is actually a linear functional, because we can see that Rn is a vector space, okay, and R is a field. So we are defining a linear transformation from Rn to R, okay, and it also satisfies our this condition. So now we can, so this is just an example for R2. So in general, this is true for Rn. That is to say that if the function is from Rn to R, so I am just writing it again so that we can have some kind of continuity, and we are defining as f of x is equals to a1 x1 plus a2 x2 up to an xn, where my x is x1 x2 xn and ai belongs to, so ai is r fixed, then this is a linear functional. Yeah, so this is exactly the same thing that we have written above. I wanted to write so that I can have some kind of continuity. Now actually we can go one more step, okay, and we can claim that in fact any linear functional on Rn is going to be of the same form. As above. So what do I mean by that? See, what is a linear functional? It is nothing but a function from Rn to R, like for one vector space to its field. So in this example it is from Rn to R. Now obviously we know that how many functions I can define from Rn to R such that it will satisfy my this condition, right? So I know that there are infinitely many functions. If I just keep on changing the values of this a1, a2, a3, an, then I can create actually an infinite number of functions or infinite number of linear functionals. So this statement, what it is saying, that it is going to be of the same form. What it says is that given any linear functional from Rn to R, that is, you take any linear functional from Rn to R in the world, however you can define it, it is going to be of this form only. It is going to be of exactly this form. Okay, so basically what does it say is that you cannot have a function from Rn to R such that f of x is equals to sin x1 sin x2, or e power x1 plus e power x2, or x square plus x1 square x2 square, like nothing. No other function can be used except this class of function, that is a1 x1, a2 x2, an xn. The most you can do is that you can change the value of this a1, a2, an. So this is what actually we are going to prove. Okay, so this is just going to be a simple easy proof. So let us define. So we are defining e1 as 1 0 0, all the elements are 0, e2 as 0 1 0, and in general I'll define ej as 0 0, the jth element is 1 and all elements are 0. So this is like the standard basis, you all are familiar with it. Now what we do is that we say that this f of ej is actually going to be aj. Okay, and what is this a? A is our this a1 x1, a2 x2, an xn, right? So we are taking this element ej in which all the components are 0 and only one component is 1, that is at the jth component will be 1 for ej, and that we will map to aj. So what does it mean? That is, what I am saying is that f of e1 is equals to a1, f of e2 is equals to a2, and similarly f of ej equals to aj. Now given g any linear functional on Rn, so basically what we will do is that we will take any random or any linear functional g, okay, which is defined on Rn, and we will show that actually g has exactly the form that we said above, that is a1 x1, a2 x2 and an xn. Okay, and now since this we have defined a linear functional called g, and now in the last class while studying the linear transformation, I said that any linear transformation actually can be determined fully by how the linear transformation is actually behaving with its basis. So the basis for Rn, we know that e1, e2, ej, these are the basis elements for the Rn. So what we say is that, okay, let us define like this, that g of ej is equals to aj, that we just said with respect to f. So the claim is that g of x is equals to some alpha x1, alpha 2 x2 up to alpha n xn, where my x belongs to Rn. Okay, so x belongs to Rn. So what we are doing here is that we are taking any arbitrary function g, we are calling that, okay, let's say g is a linear function on Rn, and what we want to show is that g of x is actually going to take this exact form. So earlier we had a's and now we are we are having alpha i's. So what I can write, that g of x is what? G of x1, x2 up to xn, right? Now this I can write as g of x1 e1 plus x2 e2 up to xn en. Now we can write it as why we can write it, if you see that if I take x1 e1, it means I'll take x1 1 0 0 0. What am I going to get? I'm going to get x1 and all the components are 0, right? Similarly x2 e2, if I do, I'll get 0 x2 and all the components are 0. So if I take the addition of all this, so similarly xn en is nothing but 0 0 and xn, right? So if I add all this, so what am I going to get? If I add all this, so I'll get x1 I'm going to get my original vector x, right? So this is by adding. So this is actually, you can write it in a bracket. So this is just for your explanation. So we'll again what happened here? Yeah, so we'll again from this step after this step. But now since g is a linear functional, right, means that I can take the scalars out. That is, I can write x1 time g of e1, x2 time g of e2 and xn time g of en, right? But what I did, I defined earlier that g of ej is actually equals to alpha j. What does it mean? That g of e1 is equals to alpha 1 and so on. So I am going to use this here again. So what I'll get? I'll get alpha 1 x1 plus alpha 2 x2 up to alpha n xn, right? And this is my g of x, and this is what we have proved. So what does it say essentially is that you take any linear transformation in the world, okay, whatever linear transformation you can think of on Rn, it is always going to have this form, okay, that is, it is going to be alpha 1 x1, alpha 2 x2, alpha n xn for some alpha i's belongs to R. Yeah, so this is one example. Yeah, so this part in the brackets that I have written, this is just for your understanding, okay? This you can write in a bracket, or like you can write it separately somewhere if you want. Now let us see some more examples, okay? Example 2. Let's say that this time we are taking the set of matrices, okay, and to the set is R. So that is set of real matrices of order n cross n, right? So the function, what it does is that it takes a matrix A and then it gives some output that is in R, and so the definition is that f of A is actually defined as trace of A. Yeah, and what is trace? You all know that it is nothing but the sum of diagonals, right? So it is easy to check actually that if you take any matrix, so just I'm going to explain it a bit. Again, you can write this in a curly bracket or something. I'm just going to explain this why. So let's say that I'll just take a 2 cross 2 example, right? So I have 1 2 3 4, and if I multiply it by some alpha, and I have one more matrix 2 3 5 6. Now if I take the trace of this matrix, so what is going, this matrix actually alpha 2 alpha 3 alpha 4 alpha plus 2 3 5 6. So what is this? This is alpha plus 2 alpha plus 3 alpha plus 5 and 4 alpha plus 6, right? So what is the trace? Trace is alpha plus 2 plus 4 alpha plus 6, that is 5 alpha plus 8, right? This is what I got by taking the trace. Now if I would have like taken it separately, let's say that so this is my function f, right? So this is what we do is that alpha x plus y. So this is my x, this is my y. Okay. So f of alpha x plus y we got as this 5 alpha plus 8. What do we check? We check that if f of alpha x plus y is equals to alpha time f of x plus y or not, f of y or not. So let's say this term we calculated and this came out to be 5 alpha plus 8, right? Now let us calculate this term, that alpha time f of x plus f of y. What is this? So alpha time, what is my f of x? 1 2 3 4. Alpha time f of this plus f of the second matrix, that is 2 3 5 and 6. So alpha time, what is f of a? F of a is nothing but the trace of a, that is 5, and f of y is nothing but the trace of this matrix, the second matrix, that is 8, and this is again 5 of alpha plus 8, right? So we here also we got alpha time f of x plus f of y is equals to alpha x plus y. So this condition holds, means this is again going to be a linear functional. So this is the second example. This is example 2, and this part is just for your explanation, just for your understanding. Yes, so we can see some more examples. Let's take one more example and this time let's take V is the space of all functions over R. What does it mean? That V is the set containing all the functions whose domain is also R and the range is also R, right? So for any f belonging to V implies that f is a function from R to R. Okay, so now on this what we can do is that we can define a linear functional or a linear transformation. We'll call it as LT, linear transformation, and this is defined over V from R. Okay, and this LT of P is actually equals to P of T, right? So okay, so we can do something here also. So like to make it more easy and to make it more understandable, let us take set of all polynomial functions. So for any element, so what does V contain? V contains all the polynomials, all the real polynomials, that is whose coefficients are also R, and when we calculate the polynomial value, it is again going to be in R, right? So what we do is that we define a linear transformation L of t, and we define it that it will take any element of V. What type of element V has? V has polynomials, right? Because V is the set of all polynomials over R. So it will take some polynomial and it will calculate the value of that polynomial over this index t, right? So for example, okay, so this, okay, so I'll say that this LT is a linear functional for each t belongs to R. Okay, so this is what my claim is. So again, for explanation part, I'll just give a short explanation that, see, you can fix t to anything. Let us say that t is equals to 1, or t can you can take 0, half, 0.5, minus 1 by 2, minus 100, whatever. Just for the sake of simplicity, I am taking t is 1. Okay, so what L of 1 does, so how does this L1 of p is defined? And let's say, so this is what, this is going to be nothing but p of 1, right? So if p is some polynomial function, let us say that, okay, x1 square plus x2 square, 2x2 square plus 3x3 or whatever, right? This is some polynomial over R, right? So what we'll do, what is L1 of p? It is nothing but you just have to place 1 in place of x. Okay, sorry, so this is a polynomial in 3D. So let me take the polynomial as 3x plus 2. Okay, because we are talking about R, that is we are talking about only one variable. If we take x1, x2, x3, it means we are taking more than one variable, right? It will be in R2, R3. So 3x plus 1. So what you have to do is that you just have to place 1 in place of x, and what you get is 5. Similarly, you can have some more. This is, let's say, p1. You have p2 as 5x square plus 9. So what is this L1 of p2? This is just 5 into 1 plus 9, that is 14. Okay, so if you check, so this is just for the explanation part. Okay, so if you check, for any t, if you try to find that L of alpha p1 plus p2, so this is LT of, is actually going to be alpha times LT of p1 plus LT of p2. So this is something that I am giving you as an exercise or homework to actually verify it. It is easy. You just have to follow the steps that we have followed previously. And anyways, if you guys can't solve it, then anyways I'll provide you the solutions. That is not a problem, but I want you guys to try. Okay, then yeah, so let us have one more example. Let us have example 4. Okay. And this time I'll take V as the set of all continuous functions on the interval 0 to 1. This is what? Set of all real valued continuous functions over 0 to 1. Now how it is different from the previous example? So in the previous example, the domain was the whole R, right? That you can take the domain value, that is the x value, was possible for all R. But here it's not like that. Here the domain we have fixed to 0 to 1, and in the previous example we only took polynomials. Here we are taking all the continuous functions. Okay, so any continuous function you can think of, sin x, cos x, e power x, x square, all the polynomial functions. So all these functions are included in this set V, and we define. Okay, so now what? So we got the set. So now to define a linear transformation, we actually need a function or a linear transformation. Let's call it as f. Okay, that is a linear transformation from V to R. And how it is defined? So the definition is that f of p is nothing but you just take the integration from 0 to 1 dt, where this p belongs to V, right? So in this case also you will find that f is a linear functional on V. Okay, so I hope that you guys already know that every continuous function is differentiable, right? I mean integrable. So from Riemann integration we know that if a function is continuous, so we can find its Riemann integration, or we can find its definite integral. And now since the space contains all the continuous functions, it means this integration is very much possible. So this is again something that I would like you guys to prove once. Okay, if you can't do it, then obviously I'll give you the solutions. Fine, this is one more example. So this is good. So far any questions on what is linear functional, or whatever examples that I have discussed? If you guys have any questions, you can write it in the chat box, or also you can unmute yourself. Any questions? Okay, so like my voice is clear, right? My video and audio all are okay, right? Can one of you just please respond?
Yes, sir.
Okay, fine. So now this is what a linear functional is. Now I want you guys to recall what we meant by L of VW. What was L of VW? It was nothing. It was the set of all linear transformations from the vector space V over F to W over F. So obviously you can define infinitely many transformations between two vector spaces. So for example, so I can define T1 from R2 to R3. One, I can define it as that, okay, T of A comma B is equals to A comma B comma 0. T2 I can define as R2 from R3, that T2 of A comma B is actually equals to A plus B comma 0 comma 0. And similarly I can define actually infinitely many number of transformations. So what was L of VW? It was the set that contains all possible linear transformation from the vector space V over F to W over F. Okay, this is you guys have already studied, and I also mentioned this in my last class. And what was the dimension of L of VW? That it was m into n, assuming that dimension of V was n and dimension of dimension of W was n. Sorry, this is m. So that is hello, is my screen visible?
No, sir.
I think there is
No, sir.
I think there is some problem. Just give me a minute. Yeah, so is it visible now?
Yes, sir.
Yes, sir.
Okay, nice. So this is what we meant by L of VW, right? So you all heard this part, right? What I was telling about L of VW. Okay, fine. So this is what we defined as L of VW. So now here also we are going to do the same thing, and all we'll do is that we'll give it a different name. So in mathematics what we do is that we take something and we try to impose some more conditions on it, or we try to find some more properties from a given set or from a given function, and we give them different names. For example, we studied functions, right? And then we saw that okay, if every image has a unique pre-image, then we will call it as 1 1. So, and if every image in the codomain has a pre-image, then we will call it as onto, right? So we call it as 1 1 function, onto function. So actually essentially what we did, we just tried to find some new property and we gave it a different name, right? Similarly here also, and like most of the mathematics we do like this only. So what we'll do here, so let us define what do we mean by V star. Okay, so let V star, this is the set of all linear functionals on V, right? So essentially we just saw, right, what is a linear functional. So linear functional is nothing but a linear transformation from the set from the vector space V to its field, that is F. So basically it is a linear transformation from V over F to F. Now what we are doing, similar to L of VW, there we took all the possible linear transformations which was available from V over F to W over F. What we did is that for this case we gave it a different name. We gave it the name V star. That is, it is going to take all the possible linear functionals on V, that is T belongs to V star implies T is a linear functional from V over F to F is a linear functional, right? And this V star is actually nothing, it is L of Vf. So there it was L of Vw because the transformations were defined from a vector space V to a vector space W, but here the transformations are defined from a vector space V to the field F. So that is why we are calling it as L of V comma F, and we gave it the name V star, and this is called the dual of V. Okay, and it turns out that this V star is a vector space. Just give me a minute. Yeah, so this V star is actually again going to be a vector space, right? And what is the dimension of V star? Can anyone guess what is going to be this dimension of V star? So the dimension of L of Vw was what? Dimension of V times dimension of W. So here what is going to be? It is going to be dimension of V times dimension of F. So the theorem, or not a theorem but a statement, I can say that if V over F is a finite dimensional vector space, so this FDVS means finite dimensional vector space, and the dimension of V is n, then the dimension of V star is also n. Okay, proof is pretty simple. So we know that for vector spaces Vf and Wf, L of Vw is the space of all linear transformations from V to W, right? And what was the dimension of L of Vw? It was nothing but m into n, where dimension of V was n and dimension of W was m, right? So similarly, taking W over F as the field itself, that is F over F. So what is going to be the dimension of L of Vf? This is dimension of V cross dimension of F. This is n into 1, which is n itself. Okay, so this is pretty simple. that if V is a finite dimensional vector space with dimension n, then the dimension of its dual is also going to be n, and this is what we call as dimension of V star. So this V star is actually called the dual of V. It is nothing but the space of all possible linear transformation on that vector space V. Okay, so this is fine. So now we can ask a question. So since we know, okay, so we can ask a question that we know that in any vector space, basis is very important, right? So we know that the basis is actually very important whenever we talk about a vector space. So the question is that given a vector space V over F and its dual V star over F, okay, and let we have a basis of V. We know what the basis of V is. So does there exist any relation between the basis of V and V star? So the question I am asking actually is that we know what V star is. V star is nothing but it is the set of all linear functionals which can be defined on this vector space V. So now I am giving you a vector space, any vector space, Rn over R, polynomial vector space, matrix vector space, okay, and I'll give you the basis of that vector space. So can we say anything about the basis of the dual space, that is V star? So with this question I'll stop today, and I want you guys to think about it, and maybe you can tell me in the next class. So okay, now we have to do the attendance. Wait. Yeah, so I'm just going to flash the attendance this, and I want all you guys to actually do it. Yeah, so it is visible, right?
Yes, sir.
Okay, so I'm just going to generate the code, and I want all you guys to actually do it, because every time I have very difficulty with this. So please go ahead and mark your attendance. Yeah, so if you have marked your attendance and if you have no doubts, so you can leave. Yeah, but before you leave, I want to tell you one thing, that the next class I'll take on Saturday, and on Sunday I'm going to take a class, like on either every Sunday or on alternate Sundays. I'll take the class from 9 or 9:30 in the morning, but that is just for the practice questions. So in that class what I will do is that whatever examples I have given you guys, okay, so I'm going to generate again, please do it fast. Yeah, so whatever examples I'm giving you as exercises, so I'll try to solve it there, and also whatever questions I find important, like from your exam point of view, so I'll discuss those problems, and there is no attendance for that class, so it is up to you whether you want to join it or not, but I'll advise all you guys to actually join it, because it will be good for your exam point of view. And also one more thing, if you guys have any previous year question papers of this like linear algebra part or the 6th semester, so you can send me that. Okay, so if you have, you can send me, so I'll also take questions from that there, and I'll try to like solve it for you guys so that you can understand all the important questions. Yeah, so if you have marked your attendance, you can leave now.
Sir,
Yes.
will you give us the notes of this part, linear algebra?
So like you guys are not writing the notes or what? No,
No, we are expecting the notes from you only.
no, like okay, fine. What I'm saying that whatever I'm writing on the screen, you guys are not noting it down, or like what?
No,
I want to know
I'm
like
taking
what is.
these screenshots, but it's not clear. That's why.
Okay, so I'll share the notes, no problem. But I'll advise you guys to actually keep the notes together, right? So like try to write it alongside. Otherwise, it is fine. Like I'll share. I have no problem in that. So I'll share the notes in a PDF format to you guys. So every Sunday I'll share of the whole week. Okay. Yeah, so you guys can leave if you have no queries then.